This video, let us try to understand what is meant by propagation delay. So propagation delay is defined as the time taken by the input to propagate to the output. So this is called as propagation delay. So let us try to understand this by taking an example. First, let us take the example of buffer. So this is buffer. So whatever the input that we are giving at the input will be same at the output also. So both input and output will be same. So here I am taking first example, that is input going from low to high. So that's why I have written here as LH. L means low, H means high, and whatever you are applying at the input, the same will be at the output also. So as input is low to high, output is also low to high. So here you need to remember these key points here. So some of the terminology I have mentioned it here. L means low, H means high, TP means propagation delay. So let us analyze this by taking an waveform. So this is the input which I am applying and this is the output which I am getting. So here I have taken as 50%. So here this is input threshold PCT rise. So this is input threshold PCT is nothing but percentage. So I am taking here as 50%. So this will be mentioned in .lib. So in the upcoming videos, I'll open one of the .lib and I'll show you how this 50% is written in particular .lib. So as we know that whatever input that we are applying, output will be same. So input is going from low to high, same output is also going from low to high. But if you observe here, output is not changing whenever input you are applying. So it is not happening at that particular instant of time. There is some amount of delay. So every gate and every combinational circuits will have some amount of delay associated with it. So this particular buffer will also have some amount of delay. So you can call it as tau D or tau PD. Anything is same. Tau is nothing but propagation delay. So here always this should be written with respect to output. Here I have taken as LH. This is with respect to output. Why? Because output is low and then it is going high. That is from low to high. So that's why I am writing here as EPLH. So this is when input is going from low to high. Now let us take input from high to low. So the same example. Now only the change is input is coming from high to low. So output will also be high to low. So whenever input is moving from high to low, output will also be moving from high to low, as this is buffer. And now here it should be written as TPHL. Why? Because initially output is high and after that it is going low. So high to low. So that's why TPHL. Now let us take another example as inverter. So we know that for inverter when input is 0, output will be 1. So whenever input is 0, output will be 1, or else whenever input is 1, output will be 0. So that's why whenever here input is going from low to high, output is coming from high to low. That is reverse of it. So input low to high, output is high to low. Same here we see the waveform here, input going from low to high, output coming from high to low. And this 50% we are taking. Why? Because we are mentioning this particular percentage value in .lib. Here we are writing as TPHL, high to low. Why? Because output is changing from high and it is coming to low. Always it should be considered at 50% value, high to low. Now we are applying input to the inverter which is from high to low. So output will be from low to high. The same thing I have mentioned it here. Input is high to low, output is low to high. Input high to low, output is low to high. And here if you observe, output is changing from low and it is going to high. So that's why here I am taking it as low to high. TP LH. LH means low to high. So remember these points. So there are some questions. Is this 50% to 50% standard or it can be changed? So generally this percentage values will be mentioned in the .lib. If you want, you can change this particular values also. It depends upon how you are doing the characterization. So in .lib it will be mentioned by using these names: input threshold PCT rise. PCT stands for percentage. So input threshold percentage rise is 50%. Input threshold PCT fall is 50%. Output threshold PCT rise is 50%. Output threshold PCT fall is 50%. So here we are taking 50% as the point. If you want, you can change this particular points also in .lib, but it depends upon how you are doing the characterization. Now let us take one of the example and try to calculate overall propagation delay. So let us take an example where two NOT gates are connected back to back. So when two NOT gates are connected back to back, it will function as a buffer only. So let us apply. Suppose if I apply input as 1, output will be 0, and whenever input is 0, output will be 1. Similarly, if you want, you can apply 0. Whenever input is 0, output will be 1, and whenever this 1 is input for the second NOT gate, output will be 0. So whatever you are applying at the input, that is coming as an output. So this is nothing but buffer. When two NOT gates are connected back to back, it will function as a buffer. So I'm taking input which is coming from high to low, and for first NOT gate it will get inverted, so it is moving from low to high, and this input will be given as input to second NOT gate. So this X is moving from low to high, so here this will move from high to low. So always if you want to calculate the propagation delay, it should be calculated with respect to input at A and output as B. So let us see this waveform now. So input is falling from high to low, and X, at the X it will get inverted, so it is low to high, and this X will be the input to the second NOT gate. So at B I'll get from high to low, simply it will get inverted. Now I'm taking 50% as an point. So for A this is a 50% point, and for X this is a 50% point. So draw a vertical line here, and here this is TP-LH. Why it is TP-LH is, here X is moving from low to high, so that's why TP-LH. Now this X will act as an input to second NOT gate, and this is the output that we are getting. Again at 50% point, draw a vertical line. Similarly at 50% point for B, draw a vertical line. Now here if you observe, this B is falling from high and it is going to low, so that's why it is TP-HL, high to low. So the overall propagation delay is nothing but TP, which is the sum of TP-LH and TP-HL. So generally you will get some numerical, so they will give you the value of delay which is TP-LH and TP-HL. By using that you need to calculate TP, which is overall propagation delay. Let us solve this problem. Same, two NOT gates are connected back to back, it will function as a buffer. So here TP-HL value is 0.5 nanosecond and TP-LH is 0.75 nanosecond. So this is the input that I am applying at A. Low, it is going high and again stable for certain amount of time and again falling back to 0. This is what I am applying at A, and X is nothing but invert of A. So simply it will get inverted, that is from high it will go to low, again from low it will go to high. Now this X will act as input for the second NOT gate and you will get output as B. So X is coming from high and it is going to low, again from low it is going to high. Now B is nothing but simply invert of X. So it will move from low to high and again high to low. So let us analyze these cases. So first I am checking for A and X. So simply draw a vertical line here, and this is another vertical line for X, which I am taking at 50% point. So if you observe here, X is changing from high and it is going to low. So we need to write this as TP-HL. So this is TP-HL. Similarly check at this point. So for 50% point, draw a vertical line, and here at 50% point, draw a vertical line. So this is nothing but TP-LH, and it should always be written with respect to the output. So here output is nothing but X, which is moving from low and again it is going to high. So that's why here I am writing as TP-LH. Now we are done between A and X. Now this X will act as input to second NOT gate where we get output as B. Now X 50% point, draw a vertical line, and B, this is the output, draw a vertical line. So here output B is changing from low to high. If you observe here, this is changing from low to high, so it should be written as TPLH. So that's why here I am writing as TPLH. Similarly, now this point 50% draw a vertical line, and here draw a vertical line. So here if you observe, output B is changing from high to low. So that's why I am writing here as TPHL. So in the two cases what I did is, earlier we have checked between A and X, and the next case we have checked between X and B. Now let us see between A and B. Why? Because A is the input, B is the output. So here A is changing from low to high. So for the 50% point, I have taken a vertical line here, and similarly at this point draw a vertical line. Now we are checking between input A and output B. So at 50% point of B, take vertical lines, and we need to write either as TPHL or TPLH depending upon the transition of B. So if you observe here, B is changing from low and it is going to high, so it will be TPLH. So I wrote it as TPLH. Similarly at this point, output B which is changing from high and it is going to low, so it is TPHL. So it is TPHL. So if you observe here, we got some values of TPHL and TPLH. Simply you can substitute the values here. So here if you observe, this TPLH is simply the summation of TPHL and TPLH. Similarly this TPHL is summation of these two. We already know the values of TPHL as 0.5 and TPLH as 0.75. So simply you can substitute here, so that we will get TPLH as 1.25 nanosecond simply, and TPHL values again 1.25 nanosecond. Why? Because they are simply the summation of these two values. So this is how we can calculate propagation delay for any given combinational circuit, or else for any kind of gate.